Hello, and welcome to Relaxing Facts. I'm Chad K, and today I will be talking about the leading theory behind the Big Bang. Each week, I share interesting stories and little-known facts on a variety of topics, accompanied by gentle, soothing music. My goal is to help you find a sense of calm during your busy day. Feel free to settle into a cozy spot and let yourself be carried away by these relaxing facts. The leading theory behind the Big Bang is known as the Lambda cold dark matter model, often written as LCDM. This model is the most successful framework that scientists have for explaining how the universe began, how it has evolved, and why it looks the way it does today. It brings together several key ideas, including the rapid expansion of space, the role of dark matter in shaping cosmic structure, and the influence of dark energy on the expansion of the universe. The model is supported by a wide range of observations, from the fading glow of the cosmic microwave background to the distribution of galaxies across billions of light years. Because it connects deeply different areas of physics into a single narrative, LCDM is considered the standard cosmological model. At the core of LCDM is the idea that the universe started in an extremely hot and dense state and then expanded. This expansion is not an explosion, but the stretching of space itself. Everything, including galaxies, stars, and even the distances between atoms, rides along with this expanding fabric. The equations of general relativity show that space can expand or contract depending on the energy and matter it contains. When scientists apply these equations to the entire universe, they naturally point toward a universe that was once much smaller and hotter. Evidence from observations confirms that galaxies are moving away from us, which means space is still expanding today. One reason LCDM is so powerful is that it explains the cosmic microwave background. This faint glow of microwaves fills the sky in every direction and represents the cooled remnant of radiation released when the universe was only about 380,000 years old. The details encoded in this radiation reveal important clues about the early universe. They showed tiny differences in temperature from one spot to another, and these variations match what the LCDM model predicts almost exactly. The size, pattern, and distribution of these variations offer a precise measurement of the age, shape, and contents of the universe. They help scientists estimate that the universe is roughly 13.8 billion years old. Another essential component of the LCDM model is cosmic inflation. Inflation is a theory that describes a brief but extraordinary burst of rapid expansion in the first tiny fraction of a second. During inflation, space grew far faster than the speed of light. This is allowed because no object is moving through space faster than light, but space itself is stretching. Inflation explains why the universe, on large scales, looks so uniform and smooth. It also explains why distant regions of the sky have nearly identical temperatures, even though light has not had enough time to travel between them. Equally important, inflation predicts tiny quantum fluctuations that were magnified by expansion and eventually became seeds for galaxies. As the universe continued expanding after inflation, it cooled to a point where quarks formed protons and neutrons, which later fused into hydrogen and helium during a period known as primordial nucleosynthesis. The LCDM model predicts specific amounts of these tiny elements, and observations match those predictions closely. This agreement is a major reason that scientists consider the model robust. It shows that the early universe behaved in predictable ways that we can still measure today. By comparing the amounts of hydrogen, helium, and lithium in old stars and gas clouds, scientists find chemical fingerprints that match what a hot, expanding early universe would create. A defining feature of the LCDM model is cold dark matter. Dark matter is a form of matter that does not emit, absorb, or reflect light, and therefore cannot be seen directly. We know it exists because its gravity influences stars and galaxies. Cold dark matter refers to dark matter that moves slowly compared to the speed of light. This property helps it clump together efficiently. These clumps form the gravitational scaffolding on which galaxies grow. Without dark matter, galaxies would not have enough mass to stay bound together, and large-scale cosmic structures would not match what astronomers observe. Supercomputer simulations that include cold dark matter produce universe-sized structures that look nearly identical to the real cosmos. The L in LCDM stands for Lambda, which represents dark energy. Dark energy is a mysterious form of energy that fills space and speeds up the expansion of the universe. In the late 1990s, astronomers studying distant exploding stars discovered that the universe is not just expanding, but accelerating. This was a surprise because gravity should slow expansion over time. The simplest explanation is that dark energy acts as a kind of negative pressure, driving space to expand faster. In the LCDM model, dark energy makes up about 70% of the total energy in the universe. Dark matter makes up about 25%, and ordinary matter, the kind that forms stars, planets, and life, makes up only about 5%. One of the strengths of LCDM is that it connects these components into a timeline that aligns with what astronomers see when they look deep into space. Looking farther into space means looking back in time because light takes billions of years to reach us. Observations reveal young galaxies forming when the universe was only a few 100 million years old. They become more complex and structured as time goes on, exactly as predicted by models that include cold dark matter. When scientists map the arrangement of galaxies across large volumes of space, they find a web-like pattern with filaments, clusters, and voids. This cosmic web is a natural outcome of gravity working on dark matter over billions of years. Although LCDM is the leading theory, it is not without mysteries. Dark matter has not yet been detected directly in a laboratory. Scientists are exploring several candidates, including weakly interacting massive particles and axions. Dark energy is even more puzzling. It might be a property of space itself or something more dynamic that evolves over time. Inflation also remains partly mysterious because the exact mechanism that caused it is still unknown. Despite these open questions, LCDM remains the best explanation because it consistently matches observations of the early universe, the large-scale structure, and the rate of expansion. Modern telescopes, such as the James Webb Space Telescope in large ground-based observatories, continued to refine tests of the model. They observed the earliest galaxies forming in the first few 100 million years after the Big Bang and study how their properties compare to predictions. New surveys measure the distortion of light as it travels through massive structures, providing detailed maps of dark matter. Instruments that study the cosmic microwave background continue to sharpen our picture of the early universe, revealing subtle traces of inflation and helping scientists narrow down possibilities for the nature of dark energy. The LCDM model succeeds because it offers a coherent story supported by multiple independent lines of evidence. It explains the earliest moments of the universe, its overall composition, the formation of galaxies, and the accelerating expansion that continues today. Even though there is much we do not yet understand about dark matter, dark energy, and the physics of inflation, the model provides a framework that fits the observations more accurately than any alternative. It continues to evolve as scientists collect more data, test new ideas, and refine theories that help us understand the universe at its deepest level. And that brings us to the end of this week's talk. If you enjoyed this episode of Relaxing Facts, please subscribe or leave a comment. I hope that you have a fantastic day, whether you're taking a moment to unwind or simply enjoying some calming listening. Thanks so much for being here. I am Chad K, and I will see you next time. Goodbye.